is to prove that every decidable language is recursively enumerable. So we take an arbitrary language L, which will be a subset of some, all the strings over some alphabet. Now, this alphabet, the strings can be written in canonical order very easily. They can be computed, no matter what the alphabet is. If we assume the alphabet is a binary alphabet, then the canonical order will be the empty string 0, then 1, then 0, 0, and so forth. But it could be actually any alphabet. And now we use this program for I equals 1 to infinity, so I runs forever. If the ith string of L in canonical order is a ith string over in sigma star, is a member of L, and we can decide that because L is decidable, then we write the value. Now we're going to get out of this, we're going to end this iteration no matter what, because if Wi is not a member of L, then we will have the answer in finite time. We'll know that. That way we can't get stuck. Now what this means is there has to be a machine that decides L, and that machine has to be emulated by this program. So it has to be put into the program. All right, now let's look over here. Problem 12, state the Church-Turing thesis. Well, that's very simple. All you have to say is every machine is equivalent to some Turing machine. All right, now we're doing a reduction. We have to do a polynomial time reduction of the subset sum problem to the partition problem. A partition problem is given a set of objects of various weights. Divide them up into two piles of equal weight. For the subset sum problem is given a set of objects. Try to find a subset whose total weight is a given number k. All right, let's suppose that we have an instance of the subset sum problem. We'll say it's in the subset sum language if there's a subset that adds up to k. Now, what we're going to do, we're going to form an instance of the partition problem. Start by letting s equal the sum of all the x's, and then we'll introduce two more x's, two more objects really. The n plus 1th object of weight k plus 1, and the n plus 2nd object of weight s minus k plus 1. Now, those n plus 2 objects here then form an instance of the partition problem, which is in the partition language if and only if it can be divided into two subsets of equal size. All right, now if we add up the weight of these objects, we'll get s for all of these by definition up to xn. We'll get k plus 1 here and s minus k plus 1 here, which totals 2s plus 2. Now, if we have two subsets of equal size, each has to have weight s plus 1. Well, suppose we could do that. Then you can't have both objects in either half because together the two of them have total s plus 2, which is illegal, it's too big. So that means one of the two halves has to contain xn plus 2, but not both. So let's suppose that we have a subset of that, which will include a subset of these together with xn plus 2. And this has weight s minus k plus 1, which means that the objects here of the original set have total weight k, because these have to be s plus 1. That way, this partition problem is in the language partition, implies that the original list is in the subset sum problem. Now, I'm not showing the converse here, but the converse is that if you have a set, you know, x3, x5, whatever, that adds up to k. Conversely, suppose that we have a solution here. That means there's some subset of the original x's that adds up to k, and we simply take that subset and throw in xn plus 1, which means it's k plus capital S minus k plus 1, or s plus 1, which is exactly half. So therefore, that this string is a member of the partition problem.